elements of the spline, and lambda there being the tuning factor for the roughness penalty of that particular system. Now, I do expect you guys to understand what the roughness penalty is with respect to it being a process by which we adjust the effective degrees of freedom of the mark, okay? We're tracking with this, get where I'm coming from here? Why would I use cross-validation? This work. I was talking to Professor Hare, if any of you guys know Professor Brian Hare. I was talking with him last night at our little faculty Christmas party, and I said, our brains have two modalities. They have input mode and output mode, right? There's an I/O switch in our brain, right? So what happens is you're sitting here in input mode, where I'm talking and you're thinking, getting it, right? You're trying to absorb the material. But then I ask you guys a question, right? And you have to reach down in your brain's transmission and try to pop it back into output mode. And what happens? You can hear the gears grinding and smell the smoke as everybody's brain goes, wait, you were talking and now you're expecting me to talk? It's like, but I've been there. I've been on your side of the room, so I'm not trying to say anything that doesn't happen to me. It happens to me even during whenever I give presentations and stuff. But why do I use cross-validation? What's the point of cross-validation at a global level?
So find the best. Go ahead.
Oh, yeah, basically, fundamentally cross-validation is so it gets to see all the data. And it's to account, I guess, for perhaps I don't know, but like different subsets of the data might be differently distributed.
That's great. That's true. I mean, factually true, and does actually contain within it the little kernel of truth that I'm looking for here, which is by looking at different configurations of the data, I effectively simulate the process of having selected a different set for training, right? So I'm going to have the process that the means and variances and the generalized characteristics of the local training sets for the cross-validation are going to be respective of a alternate world in which I had theoretically picked a different training subset, okay? The reason why I do that is if lambda works for one training subset, but if it doesn't work for another training subset, what has to happen? I have to say, that lambda is too big, or that lambda is too small, right? Each one has to be balanced for the roughness penalty relative to RSS. So what we're going to try to do is we're going to try to have the spline smoothing operation set to two different particular operations. First is the specification for a specific DF. Notice up there at the top, I can tell it what the maximum degree of freedom I want it to have is. How does it calculate that? It develops that second derivative characteristic for the number of bases within the system and says this is the lambda that will satisfy that DF for the system of S. It does so by this matrix ratio product over here, right, of the square product. This is the mechanism by which we associate the localization penalty for RSS for CV for lambda. It does this and then outputs a value for lambda that satisfies with that cross-validation as close as possible to that relative DF, usually without going over, all right? So that's usually how the algorithm is written, is max 10 DF, right? So get as close as you can to 10 without going over, right? Because we don't want to allow the system more flexibility than it's necessary, but we want to do what? Capture as much of the variance as we can, so we want RSS to be minimized. So min RSS without going over 10 DF for that particular selection of lambda. That's kind of the way in which the full algorithm is written out. You can just put in spline smooth down here in the bottom, and it will do something similar to the neural network process where it's going to do a gradient-based assessment for the multiple elements in play here. I'm going to go back and we're going to talk about something that I actually think doesn't work well until you understand that aspect of it, but it's technically before this, right? Not placement. Where do we put these, right? Where exactly do these go? Notice two things can happen here. I can move this one over, right, and create a new knot point within the system. That will make this window, right, this one technically down to infinity, right? It'll make this window slightly bigger. It'll expand its overall size, right? But it makes this one what? It makes it smaller, shrinks it as a result, because now it has less elements of the basis, right? So with some relative degree of complexity, we have now what? Two objectives to take into consideration. We have CV error, right? CV, we'll say error relative to CV at some ratio lambda. And at the bottom of this system, we can have, first, this is where to put the knots in the system, right? Where to put the knots. Which ones, okay? So I would say that the first thing I can put on the bottom here is my knot selection. Then I can have what? I can have lambda overall. So these can be individual considerations, right? What's the third one? Error, RSS for the system. So I'm actually trying to min-max those placements. How many knots I have, where the knots are placed, what the relative flexibility or degree of freedom are for those knots relative to the entire system, and the total variance capture that I'm establishing in this process, all right? We went from having, for most of our linear and multilinear systems, a couple of little knobs to twiddle, right? Now all of a sudden you're sitting in the cockpit of a jumbo jet, right? You're like, so many knobs, so many things to crank, so many variations that are possible here. And there's more than this, okay? There's more than this, technically. But we're gonna deal with this from the perspective of saying that where we place the knots, how many we have, and the relative degree of lambda is going to create that effective degree of freedom for the system. Go forward until I find the other one here, all right? This one is actually this is the payoff for everything we've been doing thus far. Notice two things at the top. First is red, which is a 16 DF spline, natural spline. And the blue one is the spline fit, leave one out cross validation operation to be able to fit this system to 6.8 DF, all right? Why does leave one out cross validation make a little bit more sense with respect to these? Well, the bases themselves are a local space. So any one given sample from that local space should be a good example relative to the likelihood or quality of fit. If you're using something like RSS for adjacency, you can say, if I leave one sample out and rotate through all of the possible samples being integrated in and out, right, as leave one out cross-validation does for the whole sample base. Remember, it's similar to that argument that we were making previously that if I take the point-wise variance of this system, I'm actually going to have a better appraisal or approximation of how the system is designed to operate. Notice here, this is a 16 DF model, and we're going to be able to get this system down to 6.8 DF by increasing lambda. What happens to it? The blue line that is constrained is no longer as wavy, right? It has smoothness that the 16 degree of freedom system doesn't, right? This is just a mechanism for making the resulting combined piecewise spline operation smoother and more continuous over the entire space, while leaving the ability for localized characteristics of the data to adjust to and approximate to the system, right? I have to start speeding up a little bit. Local regression. What is local regression? Nothing special in the effect of saying that we already dealt with it previously in some senses, right? We utilized the nearest neighbor approach in our first mechanisms of approximation. This is just the sliding window capacity for a nearest neighbor approach. Let's look at it from the perspective of and see if you guys can track with me as to what would happen if this is the window, all right? So this is the window width. This is how far to either side of the current position that I'm looking at that I'm going to look on either side of it in order to create the average relationship of the data points and establish the value at that particular center value, right? What would happen to this system if I made that more narrow? Notice these are little slopes that it's taking in consideration along the way, what happens.
So it had more degrees of freedom.
It had more DOF, exactly. So each individual system would have less constraint based upon how far it's looking on either side of itself, be less supported. So it would be more capable of making small instantaneous adjustments to the data as it's going across, capturing more of the variance in the structure. What happens if I make it wider?
So the opposite, it have fewer degrees of freedom.
Correct, it would constrain it more, all right? So one system has less constraint, the other has more constraint. The constraint is the wider I am, the more I'm effectively taking the average. You could say that the wider it is, the smoother it would be, right? Because it's averaging over a larger space. That means that if there's many samples and it adds one on one end and drops one off the other end, right? Effectively, this is like an FIFO buffer, right? So as it's moving through the system, the first element in is the first element off as the buffer fills across the system. So as it's moving forward, if you expand the width of that buffer, what happens to the averaging characteristics? One sample is not going to have as big of an impact on any relative instantaneous change as the system moves forward. So it's going to be much smoother, it's going to be much more constrained. I like to say that the idea of a momentum with respect to a rate of change of regression is related to that window width characteristic, because the wider the window is, the harder it is to turn it. It's like it weighs more, it's heavier. So you have to really crank on it to get it to move, right? So otherwise it's going to drift slowly throughout the process. You make it really narrow, it's going to be able to be moved really easy, and it's going to crank really easy. So the wider the window, the longer that particular moment arm, the slower it's going to move, the more intentional it's going to move. What's going to happen? It's going to be like a boat, a really long boat on a big wave, right? It goes up slowly and then down slowly. Small boat. All right? This is a boat going across the ocean, right? That's it, done. Congratulations. All right, so it's a cool tool. It has cool utility, but what's one of the other things that's interesting about this? Is the model really interpretable? Not really. Because each individual point, right, is just a string of points. It doesn't create any level of model continuity. It doesn't try to link model continuity. It says it's piecewise for wherever the center is of that red dot relative to the dot, the element around it. So it says for x equal such and such value, this is the current value. For x equal to one step forward from there, this is the current value, right? So this effectively becomes a giant vectorized list showing you the point-wise values along the system. This is just a long string of dots that we imply connectivity between by interpolation. So as far as parsimony goes, not much. As far as granularity, flexibility, utility for fast approximation of something that could use piecewise inputs, it's stable enough for some cases. All right, we're going to talk about generalized additive models, but we're going to do so as quickly as I'm capable of, because I want to try to make sure that I get at least half a lecture for each of the remaining topics, okay? We've run out of time a little bit. I think I ran over a little bit on deep learning. But as I said to you previously, some of the topics and concepts in trees and SVMs are going to be very familiar with respect to what we've already spent time talking about. Generalized additive models borrow from a system that we're going to be familiar with. I'm going to talk about how it works first, and then you guys are going to see what I'm talking about here. Notice there is only one feature in each of these relative regression models. So the first regression model characterizes the relational aspects of year relative to some offset or relative impact to the net change in the output of y. So it says that y, total of y, is impacted by a set of individualized functions. Notice beforehand I was utilizing beta coefficients. Beta coefficients were those linear correlations between the elements. Now I'm utilizing full functions, f functions, right? What I'm trying to do, or trying to make an argument for here, is that if you treat each individual component or feature as if it is its own independent regression, you can actually characterize it with saying the impact of that feature relative to the total net change in the output as a result. So it says that if the year is 2003, right here, it says this would be the 0 point, right? That there would be no rough impact on the system. But it says at year 2003, the system was approximately impacted by a factor of -5, by it simply being that year, right? What are we talking about? What does this mean? The idea that the year impacts the system as a net positive or negative relationship. Well, the generalized economic conditions affect somebody's wage. So the argument would be that in 2003, wages were overall suppressed on average by a factor of -5 in terms of whatever this value of y is, something like k per year. So this is going to be creation of a model that is a correlate of a relativistic change in y. Interesting, right? We were doing it as whole change in y previously. Now we're doing it as relativistic change in y with respect to this. It's not even base. Net change of this factor relative to all factors in the system is the ratio of change that this factor independently contributes to the overall system. What happens when you add all of those marginal probabilities for naive Bayes together? You should get the full product, 1, the output of the whole total likelihood of the system. So the cool part about this is now I can model each of these features utilizing whatever modeling methodology I like. I don't have to use a high degree polynomial. I don't have to use a spline to model year. I can just use a linearity. So it's a linearity. Piecewise linearity for this particular system. It needs spline. This one needs spline, but it could also just be poly. Right? You don't need to have individual piecewise operations. You could just do one poly fit for the whole system, maybe 3rd or 4th degree. That's allowable, right? But you could make it further granular by putting something else in. Or you could do it as a step function, or you could do it as yada, yada, yada. I can do whatever I want. Notice over here, education is dealt with in an entirely different way. Why? What are we looking at across the bottom? What's likely to be the factors with regard to education? Give it to me. Didn't finish high school. Finished high school. Bachelor's degree, master's degree, PhD. Right? It's what? Categorical data. I am now characterizing, using a whisker plot, right? Categorical data alongside of multilinear regression and linear piecewise regression. I've dealt with each feature using entirely its own methodology. Yet, whenever I add them together, if I characterize them relative to their relative contribution, relative total net change in that system, I can create something that is, as you'd say from a certain perspective, greater than the sum of its parts. So the sum is, the whole is greater than the parts, effectively, the individual parts. Okay? This is just some of the methodology which we use, right? We can input within the LM space to model wage from NS using year and what? Now we have DF. We're going to fit NS for year DF, natural spline. Actually, that one is natural spline, but it probably has a high lambda because it's effectively fit for 5DF for the 4-year ranges that were provided. They might as well be linearities, okay? NS for age with DF5, this is effectively saying determine number of knots necessary, but do not go past the total degree of freedom of 5. And then at the end of it, it's just added on education. As we said previously, since education is just categorical in the space, it's just a raw numerical. I'm not even utilizing any kind of function to fit it. But I'm utilizing fit LN function operation in order to be able to have multiple elements treating the elements independently as their own fitted linearities for each individual data point. This assumes independence, like I said, just like the naive Bayesian construct, but as a result, whenever we plot these systems, we get systems of equations that show how these work utilizing plot generalized additive model framework. These have some uses for mixed term operations that can be utilized alongside the analysis of variance operations, or ANOVAs. We don't talk about those in here, but if you take an advanced statistics class, they'll talk about how you can use variant and covariant matrices to compare and contrast the performance of all features relative to every other feature, right? Basically that pairs operation we do when we plot, it runs that set of values for all the features in the system to compare their utility of every single value to every other value in the system, right? That's crazy good if you have a lot of points and you're not really sure which ones you want to use. We can use GAMS for classification, but the big difference between classification is that the output of the system, rather than a function of the total output, y is what? The log likelihood. The likelihood of p of x relative to 1 minus p of x. It's the specific class relative to all class of the system. Notice we get the same data, but we get different shapes and different inclusions. The characteristic that comes here for this one might be, for instance, age and then education. But if this one is the likelihood of wage exceeding 250, right? What does this say? Likelihood of wage exceeding 250? You don't need to include people that haven't finished high school, right? I don't need education of not high school, because your likelihood of getting more than 250,000 a year if you didn't finish high school is nil. So the system will actually remove features in some cases that are unnecessary if that categorical relationship does not support a likelihood. What's the other consideration? If no instances were found within the system, its likelihood or its log likelihood product is 0. So it's going to say it cannot be in the system because no probability of it was found within the data, and it will get automatically dropped by GAM, the Generalized Additive Model Framework. Okay, typically. It can happen that it doesn't, but notice here, education, comma, family as binomial. Family binomial is the relationship of creating in or out relationships. So it's just saying family, the family of relationships being modeled and characterized by generalized additive model is a binomial distribution. You're in or you're out, right? Success or fail. You can create other types of distributions, but you have to characterize the family of the distributions in order to make them make sense, okay? I'm done with GAMS. Let's go ahead on to trees. Hopefully, I don't have to, but if I do have to, I will do SVMs as a supplemental video lecture for you guys. Hope not, sorry, but I might have to because we might run out of time, but I don't want to skip it. However, it'll lighten its impact on the final exam. I've never asked a lot of questions on it anyway because I think it's pretty complex, but I want to introduce it to you anyway because it's a cool trick. But I said I don't want to cheat anything with regard to trees, and I've got 8 minutes now, and then one more lecture. I might go ahead and actually do that SGM lecture ahead of time and just do trees on Friday. So I'm trying to do the best I can for you guys. I think I either missed one more lecture than I anticipated or got short on some stuff. But so tree-based methodology is relatively straightforward. All right, let's see how far we can get from it. We say that tree systems are a method that operates via binary fission. We break things in half, either above or below a threshold. That process implies the nature of something that is called stratification, right? So at the root of the tree system, we have some value consideration. And if you were to look at this, it's like driving through the mountains, and you have different layers of sediment up on the wall, right? How those things sort of settle down onto one another. You can think about it from the respective aspect of, like, if you're up here on the top, what's most important to you, right? It's whatever's closest, right? It's not the things that seem are the deep in the ground. Those things are far less important to us, unless hey, I don't care if you're an archaeologist, you quit. But
I was just thinking about gold, platinum.
You're old.
Gold.
You said gold. I thought you were saying you're really old. Yeah, you're really old. This stuff might be more important to you, right? But the reason why I'm saying this is importance, right? Let's break the word down, right? Important. Have anybody ever heard of a sign's importance? It's a notion of its capacity to predict something, to tell you the likely future, right? The things that are far below the ground are far further in the past, and thus probably less capable of prescribing to you what is going to happen in the near future, right? What's on the ground now, or what's slightly under the ground now, is the more recent past and is more effective on the subsequent future. So if you're thinking about it, if we were to rotate this up on its edge, right, as we're moving through time, some characteristic, we extrapolate, it is the local characteristics of the system that are going to be most informative to us as to what's going to happen. They're the support for the next consequent elements. Let's consider these based upon the idea of features in and of themselves. These are just the aspects that are descriptive of the data space. So if I choose things that are float to the top with respect to this system, then I'm going to utilize features and factors that are going to break apart those elements based upon some threshold, right? Such that I would say a value greater than X, right? Might go to the right side in that particular case. So we say that that process is called stratification or segmentation. We break an area up into segments or regions, and then we treat that entire region as one functional basis or region of interest, ROI. Decision trees are one methodology. We're going to talk about a variety of different methodology, and we say that simple trees are really good because they're interpretable, because everyone's done a flowchart. They are competitive only with relatively rudimentary systems, linearities and strict low dimensionality modeling systems for regression frameworks, and something like logistic regression for classification purposes, okay? Anything beyond that in terms of complexity for machine learning models, trees are going to get blown out of the water. They do not perform as well. However, one tree, just like we're dealing with the GAM system, one tree is not necessarily all that is possible, right? A forest can be greater than the sum of its trees. So we're going to utilize processes that are going to be called bagging, random forests, and then boosting, which boosting is going to take advantage of the projection capacity of alpha, or the bootstrap, right? So we're going to create multiple different subsets of the data with bootstrap, and from those we're going to train multiple different trees. And random forests, bagging random forests and bootstrapping, which is then called boosting with trees, are methods to be able to grow multiple trees that are going to combine our total system, right? So let's look at how we do this. Let's look at a single example, and then we'll come back to this next time. I can get through this example for regression. Interestingly enough, trees can be utilized for regression, but similarly to step functions, they're a massive reduction in total system complexity. What are we looking at here? We're looking at baseball hitters' salaries relative to two factors of interest: number of years played across the bottom and number of hits, which is their relative game performance, right? So we say that it really doesn't matter how you perform. On average, you can be a great player or relatively okay player, but if you played less than 5 years-ish, you're likely going to be getting roughly the same salary. Now, there are a couple examples here and a couple of exemptions. Notice two things. First and foremost, these guys down here, okay? I want to know who their agent is. I want to know their agent because I want to get that guy on the line, okay? I can play baseball, right? If I don't have to have any experience and I'm not good at it, right? I'm zero or they're at, okay? And I get paid as much as somebody that's been playing for 12 years and is really good, right? Man, you must be awesome, okay? I'm just saying, your agent is a miracle worker or has signed a pact with the devil.
I say if you can have a beer bet on a pro level team, it's not really a sport.
you go back to people like Babe Ruth. I mean, come on, the guy was not exactly a specimen of physical fitness, but he could hit a ball. So let's look at how we're going to break this up in order to get maximum characterization out of it. We said that we wanted to stratify. We wanted to consider the feature that was most descriptive of characterizing or placing the number of samples within a box, a bounding range, that made those samples most self-identical, right? The homogeneous within the space described. So we characterized this and said that if we make the boundary or the constraint box around the outside of that sample data values less than 4.5, tracking us down to an average of 5.11, right? I'm assuming this is millions of dollars paid. I don't know, this is baseball, right? So it's probably millions. But we just characterize first and foremost, it does not matter what your performance is, right? If you played less than 4.5 years, you're likely going to be more correlated with a 5.11 million value. What does this look like structurally? Well, we create these regional boxes. Again, now I'm using R rather than C. Why am I using R? Because the cut points create a bounding box, which we call the region of interest, or region in general. So we say region 1 is defined by the assignment of values or assignment of samples for players whose value of years is equal to 4.5. So this is saying assignment in X given years less than 4.5. And then we have a second consideration, right? Effectively, we've taken region R1 and we cut off all of the new players, the rookies, from the system and said, on average, they're going to have a payment level of that 5.11. Now, how I'm doing that is through a sort of exhaustive internal process. I take the average of that whole system and then I compare each individual value to that average to get the aggregate residual square error as a result of how far away on average on average and in total, both of those can be considered. How far away on average the individual sample is and how far total all of the samples are in the system away from the mean, which has been established by taking the average of those elements that are constrained within that box. So where I decided to place that value 4.5 is the key factor here, right? Why did I not pick 4.6? Why did I not pick 4.4? Because I wanted to try to get as many samples, right, which would characterize as large of an area as possible, which would make my understanding of that space better because more examples, more samples were taken into consideration. However, I didn't want to make it so big that it started taking samples that were uncorrelated into that space, thus shifting the mean and increasing the relative square error for that spatial definition. I have this region that's less than 4.5, and I have another region that's greater than 4.5. Notice, I've broken it up on another axis now. I've broken it up according to performance, right? I say 117.5. The first consideration is just to cut off those samples that are most easily defined by a single internal constraint. The second system is then to further isolate or further push individuals into smaller and more localized and more descriptive categories, right? We go from the general process to the specific by creating smaller and smaller regions, by drawing these lines in the decision space and selecting those lines based upon mechanisms like cross-validation and other scaled treatments that will allow us to find a good size of a bounding box for the space such that we can maximize what's called the purity of the sample, right? So we want to make sure that the elements within that space are more similar to each other than they are to their adjacencies, and that there is adequate description and separation between those elements, so much that we create the biggest box we can to make the most descriptive for future capacity, but not so big as to forget the ability to try and create a unified approach to the understanding of the system, right? We want to try to describe something that has to be useful in its descriptive characteristic, but not so small as to cause a problem that we're going to talk about, which we've already talked about in many other spaces. What's the problem making the box too small?
Overfit.
Correct. Absolutely correct. It is overfitting. Why? Because if you only have one sample left in the tiny little box at the end of the process, that means you're only making your appraisal for that local region based upon that one data point. What is the likelihood that any other data point within that region is going to have exactly that same value? Right? It'll drive the error to zero, which is not what looks nice. But when we start comparing the training and testing data, when we start comparing new data, the utility of the model is assessed as just like every other model we've worked with, assessed on performance of new data being entered into the system. I have a sample that we'll run through here that has real runtime on the website, and we'll talk a little bit more about the characteristics internally about the terminologies and the workflow of the models. Like I said, I will probably try to do that supplemental lecture. If I can get it done, I'll try to get it done later today. But we will finish up with trees, and I will supplement you guys with another lecture on SVMs. In the past, I've actually done the deep learning lecture as the supplemental one. So if you take into consideration how much time we spend on the deep learning stuff, I'd probably flip the script on that a little ways. But I consider that so important as to what you're likely to get in contact with out in the future. You might see an SVM somewhere, but you're much more likely to see a deep learning system. So we'll reserve SVMs as a archaeological, they're at the bottom of the pile, archaeological exhibit that we're gonna look at and say, here's a cool trick we can use that's related to some of our understanding. But I'm only gonna require you to remember a couple of like key terms from that for the final, and I'll make sure to highlight them real clearly to let you know what things I'm super interested in there. And hopefully that will help you for your final project as well, just to be able to explain what those SVMs are doing and why they seem maybe in some cases to be outperforming other methodologies. All right, sorry for taking a little extra time. Thanks for your patience. I'll see you guys soon.
So on the timeline, are we gonna be allowed to have a cheat sheet? Like with the new-
Yeah, you'll be able to have a double-sided 8.5 by 11, just like you did in the beginning. You can take your first one and run on the back of it. That's why I didn't collect it. So yeah, you can use the back side of your first note sheet as this, write the second half of your notes on there, or construct a new page. It's all right, you can do what you want. I'll put a post on Canvas for that. I always forget to post what I forget to do. I mention it in class, but then people forget.
Yeah, I think I should start making it now.
Do what?
I think I should start making it.
Yeah, I imagine you should, because I honestly think about it whenever you're doing your final project. If you're doing your final project now, that's a good place to start. Because while you're going through your final project, you're kind of doing a review of the whole class anyway. So I think it's like, hey, you can put what equations you're interested in seeing and estimations and those sort of things. So I'll post that, but you guys can tell your friends to double-sided A4, 8.5 by 11, whatever either one. So, yeah.
So another thing, so the last chapter you're going to supplement as a video. So that's the things that you discuss in that video. We are going to study only those.
They'll be on the final.
Huh?
They'll be on the final.
Only those will be on the final.
All the things I discuss in class. I mean,